Welcome. In this video, we are going to discuss about the hypothesis concerning several proportions. In the previous videos and all, we have we started a discussion concerning the proportion. We had a population, okay, and we expect some of the population to have some attribute and the remaining does not have the attribute, okay. And we went for the case with two population, like in both the populations we had one certain set of members who have some attribute and the remaining does not have, right? So what if we have n number of populations of the same thing? Okay, this is what we are going to consider in this thing. Okay, when we have, like, okay, from the population 1 we take a parameter p1, okay, and from population 2 we take a parameter p2, and here we assume we have k different populations. Okay, so from k different populations we have the parameters p1 through pk. Okay, here the hypothesis H naught would be to test whether all these population parameter are equal against the alternate hypothesis that they are not equal. So when we try to say they are not equal, even if one is not, supposing k minus 1 are equal, and if the one is not equal to this, then also it is the case of our alternate hypothesis. Okay, so from all this population, of course we take what a sample would be taken, so that one we denote it as x1 x through till xk, and the number let us denote it through n1 through nk. Okay, so if we define each xj, each are independent binomial distributions. Okay, and when the sample sizes are large enough in all the k cases, what we have is we have k different standard normal distributions approximately. Okay, when you make when you have this one, and the square of these standard normal distributions, the sum of square of all these distributions will become a chi-square distribution. Basically, chi-square is what? Chi-square is summation j runs from 1 through k, and that is zj square. Okay, if we take that as zj, it is zj square, the sum of these things. It is the chi-square random variate with parameter k, that is the degrees of freedom k. Okay, suppose the null hypothesis is true, therefore that is chi-square would be equal to this one. Okay, here this numerator, and we assume that all these proportions are equal to k, we just substitute that as k and simplify it in this form. Okay, and when we multiply this quantity with the first one and with the second one, we get the first quantity as it is, whereas in the second quantity we just make some modifications and write this one. Okay, that is like when we proceed further you will understand why we have written like this. Okay, and further, uh, here when we are interested in checking the null hypothesis that they are equal, and here we are saying that they are equal to some p, but we may not be interested in the value of this proportion. Okay, we are just interested in checking whether they all have same proportion or not, no matter what is the value of the proportion. In that case, we consider the pooled estimate for the parameter p, that is this one. Okay, so even when we discuss for two two population proportion, even then we had x1 plus x2 upon n1 plus n2. That is, we may not be interested in knowing the value of the proportion, but we are interested in checking the equality. In that case, we can make use of this one and do the remaining calculation, so we get something of this form. This is a chi-square random variate with k minus 1 degrees of freedom. But if you proceed with exactly with p's, and if you are interested in the value of p as well, This becomes a chi-square random variate with k degrees of freedom, but when you use the pooled estimate, you will have k minus 1 degrees of freedom. Okay, suppose a sample data is given like this. So this x1 through xk are the members in each population having the attribute. Okay, so of course, if n1 and n1 through nk are the sample sizes from each population, of course failure would be n1 minus x1. Okay, we just make the total, and the statistic that we use to calculate these things is given up by summation I runs from 1 to 2, because two options are there. Okay, and j runs from 1 to k. Oij minus Eij square upon Eij. Here, this Oij denotes the entry in the ith row and the jth column. Okay, similar to Eij. Okay, which is similar as that of Eij. And this Eij are called as expected cell frequencies, and Oij are called as observed cell frequencies. And this Eij is calculated. Okay, when we proceed further, I'll tell you the way in which we can calculate all these things. Okay, next we are moving further for analysis of r cross c tables. So here if you see, we had only two rows. Okay, in general. Okay, so this is concerning the hypothesis of several populations. Okay, so in general we may have any number of rows and any number of columns. So that analysis, that table is known as R cross C table, and the analysis of those things, that is what we are going to do. So there we have seen the two-way classification of table with two different attributes. But there may be a case which has more than that. Okay, so the row and column, based on the row and column, we will do all the things. So in this case, we will have R multinomial populations with each trial permitting C different possible outcomes. So basically, you can imagine a general table have any number of rows and any number of columns. Okay, now that, like for example, people in India can be classified based on their religion and literacy. Okay, and in a group of in a company, a group of employees based on their educational qualification and performance in job, there are many more, right? Now we will have to check the hypothesis for independence. Okay, that is whether there is any dependence between the two attributes or not. So one attribute is specified in row wise. So when we say attribute, there may be any number of attributes. Okay, in the proportion case, there we had only two, either having an attribute or not having an attribute. Okay, but when you say when you have several options for the attribute that you are dealing here, religion and literacy rate, that we have taken two attributes. Okay, based, like there are many number of religion. So when it comes to religion, there can be many possibilities, right? So that is what we are going to do. Like, is there any dependency between them or not? That is what we will test. Okay, a large sample would be taken. Okay, like as I showed, we will have observed frequency and expected frequency, and based on that we will do all the calculations. Okay, okay, here the null hypothesis, it attributes represented by the two-way classification are independent with some level of significance alpha. Alternators, they are not independent, that is they are dependent. Okay, and to calculate the expected frequency, it is Ni is the row total, Mj is the column total, and N is the total. Okay, and here the chi-square statistic would be this, and we will reject the null hypothesis. Sorry, we will reject, yeah, we will reject the null hypothesis in case of this, and the parameter is nu, which is r minus 1 multiplied with c minus 1. Okay, in that case we had only k minus 1 degrees of freedom, because r was 2, so it is 2 minus 1 is, which is 1, so 1 times of k minus 1. That is what we had there. Here Let us see some examples. A large electronics firm that hires many workers with disabilities want to determine whether their disabilities affect such workers' performance. So basically, they the company hires some persons with disabilities, and they'll have to check whether the disability is affecting their work. Okay, we are asked to use the level of significance 0.05 and the data given below to decide whether it is reasonable to assume that the disabilities have no effect on the worker's performance. That means there is no relation between them, right? Okay, so here if you see, the first thing that you have to do is to uh, to make the same total, like make a table. Okay, and you will have to calculate this n1, n2, n3 values, as well as m1, m2, m3. Here we have three rows and three columns and the total. Okay, so this n1 is the sum of this 21 plus 64 plus 17, and that is 102. Okay, in a similar way it is 16 plus 49 plus 14, which is 79, and it is 29 plus 93 plus 28, which is 150. Okay, m1 is uh, just a minute, let me write here. M1 is 21 plus 16 plus 29, which is 66. So in a similar way, we can very well calculate M2 to be 206 and M3 to be 59. Now, if you make, if when you have to calculate this N, this can be either 102 plus 79 plus 150, or 66 plus 206 plus 59. Both are 331. So this way we calculate this n1, n2, n3, and m1, m2, m3 and begin. Okay, once it is done, you will have to calculate the upside, uh, expected value. Okay, that eij, expected frequencies, we'll have to calculate. Whatever is given in the table is the your okay, here if you see observed ones. Okay, o11 is 21, o12 is 64, o13 is 17, o21 is 16, o22 is 49. So in this way you can understand these are the given observed frequencies. Now let us calculate the expected ones. So in order to calculate the expected ones, that is E11 means it is N1 multiplied with M1 divided by whole N. So that is basically 102 multiplied with 66 divided by 331, and this will give you 20.34. Okay, here your E12 is 102. So the corresponding row and the corresponding column you will have to multiply, divide by the whole thing, 331. So this is 63.48. Okay, and similarly here it is 102 product with 59 divided by 331, which is 18.18. Okay, in a similar way, if you calculate here, it is 79 product with 66 divided by 331, which is 15.75, and here it is 49.17. So in a way, in this way, if you calculate the entire table, you would have these quantities, right? So this is the table that you have now. To proceed further, so to proceed further, what is the thing? We will have to note down the test statistic. Okay, so here we need to find out, like, the test is, the null hypothesis is workers performance and disabilities. independent. There is no relation between their disability and their work performance. We are testing this null hypothesis against the alternate hypothesis. They are dependent at 0.05 level of significance. And what is the test statistic? The test statistic is chi square, which is summation I runs from 1 to r, summation j runs from 1 to c, okay, observed minus expected whole square upon eij, right? Okay, now that it is our duty to calculate these things, so for which what you can do is that as a rough thing, inside the table itself you can very well like try and identify the calculations. So if you okay, I hope this is clear. So you will just have to find the difference of these two things and square it and divide this by this quantity. Okay, so when you do it for this table alone, you would get 0.0214. So when you do it for this thing, so observed minus expected whole square divided by expected, if you do it, you would get 0.0043, and it is 0.0766, and here it is 0.0039. So this one you can do it as a rough thing. Okay, so if you calculate this for every entry, then it would be easier for you guys to sum them up as finally. But it is not mandatory to write that in the table, but I'm doing it as a rough thing so that when I add, I can add it in a proper way. Okay, so this sums up to 0.1957. When you add all the entries, you would get 0.1957. Okay, here the parameter for the table value chi square alpha is, which is r minus 1 multiplied with c minus 1, which is 2 times of 2, which is 4. Okay, so from chi square table, your chi square alpha value is 9.49. Okay, since chi square, the calculated value is less than chi square alpha, we will have to accept the null hypothesis. What is the null hypothesis? That is, workers' performance and their disabilities are independent. Okay, moving further, here a study, okay, in this problem, a study is made of the failures of an electronic component. Okay, there are four types of failures and two mounting positions for the device. The following data have been taken. Could you conclude that the type of failure is independent of the mounting position? So again here, if you notice, your H naught is the type of failure is independent of the mounting position. So we are making this one against the alternate hypothesis that the failure is dependent of the mounting position. Okay, so here we have all these things, and if we just make the total, we would get n1 is 95 and n2 is 39. Okay, and your m1 is 26, m2 is 63, m3 is 24, m4 is 21. Okay, now we can very well calculate the expected frequency. So that one, let me write it in blue color. So it is 18.43, 44.66, 17.01, 14.89. So how do we calculate this 14.89? It is 95 multiplied with 21 divided by 9. Okay. So here it is 39 multiplied with 26 divided by, sorry, this is not 9, and this total n is 134. So we'll have to divide this by 134. Divide by 134, which is nothing but 1.16. Similarly, here we get the 18.34, and it is 6.99, and it is 6.11. Now you can very well calculate observed minus expected and all those things. So if you get back here, uh, the parameter is what? That is denoted as nu, which is r minus 1 multiplied with c minus 1, which is 2 minus 1 multiplied with 4 minus 1, which is 3. Right? And the test statistic chi square is given as what? We'll just have to make the difference of these two, square them up, and divide this by the expected one. So if you just calculate it, you would get it as 15.9883, and from this you can calculate from table your chi-square alpha is 7.815. So here your calculated value is bigger than the table value. So this forces us to reject the null hypothesis. Therefore, the type of failure is dependent on the mounting position. That's it. Thank you.